There is a deeply held assumption in how we design our world. We naturally believe that if we just provide a system with complete data, it's automatically going to make the best possible choice. But what if it doesn't? What if the very act of seeking that perfect accuracy is the exact mechanism that guarantees a catastrophic failure? Today, we're going to explore a hidden structural force. It's a force where the rational pursuit of perfection doesn't just delay a system, it systematically paralyzes it. We have to begin with a universally accepted truth, one that guides everything from corporate strategy to the automated software running in the background of our lives. The premise is incredibly simple. Gathering maximum information yields the most optimal decisions. We assume that if we just have more data points, more sensors, and more historical context, our system's accuracy is going to approach absolute perfection. But here is the really disturbing contradiction that emerges in reality. When you actually flood a complex system with total information, it doesn't become flawlessly efficient. It crashes, it freezes, it just completely stops. The pursuit of perfect accuracy fundamentally halts the system's ability to act in the present moment. The consequence of this contradiction is entirely structural. See, the system successfully gathers total information. It sees every single variable, but it is entirely unable to execute a response within a natural, required time frame. It observes the disaster perfectly, but it's just too slow to step out of the way. This tension perfectly illustrates the structural constraint the system faces. On one side, we have rapid action that risks error, fast but inaccurate. On the other side, we have perfectly calculated action that arrives way too late. The system is caught in a profound trap, forced to navigate this brutal space between speed and certainty. To really understand how this trap closes around us, we need to look at how this plays out mechanically. Section 1. A simple physical system. Let's move to a tangible, historical example so we can observe these forces in motion. We're going to step away from modern digital networks for a minute and look at something purely physical, a mechanism that has persisted for centuries. This is the ancient Alexandrian float valve, invented in Egypt around 270 BC. It's an incredibly simple, persistent physical system. Its absolute only job is to maintain water at a constant level in a tank. Step 1, the water level rises. Step 2, a floating mechanism on the surface rises with it. Step 3, the rising float physically pushes a valve closed. Now, the crucial point is exactly how these steps connect. The rising water inherently provides the exact physical data needed to close the valve. The output of the process, the water level itself, is routed right back as the input that controls the process. It forms a really basic, continuous, and unbroken circuit. In its absolute simplest form, this circular chain of cause and effect operates fast and without hesitation. If the water drops, the valve opens immediately. If it rises, it closes immediately. It's a highly effective, fast-acting system precisely because it only looks at one single piece of data, the immediate physical height of the float. It doesn't overthink, it just acts. Section 2. The cost of observation. But what happens when we demand greater precision from this physical system? What if we decide that measuring just one spot on the water's surface isn't accurate enough, and we suddenly want a truly perfect reading of the entire tank? Well, we start with our baseline state, one sensor, one float. It allows for instantaneous action. Yes, the water might ripple, and the valve might close a fraction of a second early or late based on a localized wave, making it slightly imperfect. But it's always fast. It keeps the tank from overflowing. Now we increase the complexity. We add 10 sensors across the tank to account for waves and temperature changes. Suddenly, the system must reconcile conflicting data points. Sensor 3 says the water is high, but sensor 7 says it's low. A processor now has to average these readings before physically adjusting the valve. And right there, a microscopic delay is introduced. Let's escalate the input drastically. 1,000 sensors. We are now capturing the barometric pressure, the precise viscosity of the fluid, and the microscopic ripples in literally every corner of the tank. We have a massive surge in the volume of data that the system is now completely forced to assimilate before it is allowed to move the valve. And this isn't a gradual slope. It's a geometric increase in processing load. As the volume of information grows exponentially, the time required to process it and actually execute an action expands right alongside it. The system is choking on its own awareness. And here is the physical consequence of that delay. Because the system is waiting for the computation of 1,000 sensors to finish, the physical valve just sits completely still. The water level begins to oscillate wildly. It drops too low, then it surges way too high, threatening to overflow, simply because the valve is perpetually stuck in the waiting room of data processing. We can now actually name this specific behavior optimizing. When a system insists on finding the absolute best, most perfect alternative across every single variable, it traps itself. The system isn't broken, it is simply obeying its mandate to find a perfect solution, rather than a solution that is just good enough to prevent a flood. Section 3. The feedback trap. We are now moving into a phase where the system's own architecture makes escape absolutely impossible. The deeper it goes into the data, the tighter the constraint becomes. As the gap widens between this massive volume of incoming data and the system's processing tools, a distinct behavioral pattern emerges. The system defaults to suppressing its decisions. By freezing the valve and doing nothing, the system unconsciously attempts to preserve its existing options and avoid making a mathematical error. Action is suppressed because the fear of an incorrect adjustment basically outweighs the urgent need to act in a timely manner. Think about it. This entire structure was designed to use an output to reduce error and bring things back to a stable baseline. It's built as a negative feedback loop. But the tragic irony is that it is now choking on its own self-correcting data. The very mechanism designed to maintain stability is the exact mechanism tearing the stability apart through over-calculation. And that locks us into this ultimate condition, analysis paralysis. The exhaustive search for certainty, the relentless drive to eliminate all risk and all error, paralyzes forward motion completely. The system has analyzed the water tank so thoroughly, so completely, that it has locked itself into an irreversible freeze. The decision is made much too late, and the tank overflows. This brings us face to face with the ultimate structural trap. On the left, we have extinct by instinct, making a hasty, localized, fatal judgment without enough data. On the right, paralysis by analysis, acting too late because you waited for perfect data. The system is fundamentally forced to choose between these two extremes. And by designing our systems to rigidly avoid the former, we structurally guarantee the latter. Section 4. Structural inevitability. We really need to stop looking at this breakdown as a glitch. We have to see it as a flawless execution of the system's core design. The overflowing water tank, the wild oscillations, the paralyzed processor, none of this is the result of a malfunction or broken code or human error. The system did exactly what it was instructed to do. It gathered all the data, it weighed every variable, and it refused to act until the optimal calculation was complete. The inability to act is an unavoidable, hard-coded consequence of choosing optimization over speed. You just cannot increase the depth of observation without proportionally increasing the delay of the output. The delay is not a side effect. It's the structural tax levied on the system for the privilege of being accurate. The system was never failing. It was following its structure. Local, rational optimization for perfect data dictates global, inevitable paralysis. We build our systems to be perfectly accurate to avoid failure. But in the end, failure is simply the cost of perfect accuracy.